Okay, thank you. Hello, everybody. So, oops. So this is a retreat about quantum technologies, and I will show you exactly that. I will show you how we can use entangled photons to do something better than we can do with the classical light. Okay? So the useful thing that we want to do is to measure optical phase. What do I mean by optical phase? So consider a thin birefringent film that acts differently on different polarization components that are passing through it. So we are working in the circular polarization basis, where R and L denotes the right-handed and left-handed circular polarizations. And assume that this film adds a phase of theta to the L component relative to the R component. So if we transmit a photon polarized H, it will gain a phase of theta to the L component. And now when we project this state on a linear polarizer and measure the intensity will scale as cosine theta. Okay? And from measuring the intensity, we can deduce theta. The precision in which we can measure theta is given just by first-order Taylor expansion. It is given by the error in the intensity divided by the slope of this function. So the slope here is at the steepest point is just 1, and the error in the intensity is statistical noise. So if we have n photons, the error will be 1 over square root of n. And this is the accuracy, and this is known as the classical limit, okay? Or sometimes it's called the short noise limit. It turns out that if we use entangled light, we can do better, okay? If we take those n photons and put them in a superposition in entangled state of n times r minus n times l, now when this state passes through the thin film, it will obtain n times theta. And when we project this state through the polarizer and measure the coincidence rate of n photons, the function will scale as n times theta. If we draw this function as a function of theta from 0 to 1, we will see more oscillations, and essentially the steep becomes sharper. And this translates to a better precision in theta. So from the derivative here, when we differentiate cosine n theta, we obtain a factor of n, and we will result with precision which scales 1 over n. So it's a square root of n times better than the classical case. Okay, so we want to demonstrate exactly this. We want to generate the state, transmit it through a film, vary theta from 0 to 1, and observe those oscillations. So the motivation, I think it's rather clear. So if we measure the phase with high precision, so we actually measure any other magnitude that's proportional to the phase better. So it's those parameters are the thickness of the film, its refractive index, its birefringence. So the example I like to give is the example of a phase contrast microscope, where if we measure the phase very accurately, we can enhance, see smaller features in some biological tissue, for example, that we are looking at. So the source of the entangled light, in our case, is a semiconductor quantum dot. So we have a dot embedded in a semiconductor. We define a z-axis perpendicular to the semiconductor. And this quantum dot can confine charge carriers, various charge carriers, holes, electrons, pairs of electron and holes, excitons. And each such occupation forms a two-level system. This two-level system, I will call it a ground level spin, okay, and denote its state as up and down. So the protocol for generating an entangled state is as follows. sorry, let me mention that so each such ground level spin has also an excited level spin, which is just adding additional electron hole pair to this occupation. And a very important thing is these two states are coupled with the optical transition, which obeys selection rules of circular polarization. It means that down ground level spin will couple to excited down spin via left-handed polarization, and the up spin will couple to the up excited with R polarization. So to generate the entangled states, we first initialize the spin, the ground level spin, in a coherent superposition in up minus down. Then we excite this spin with an edge polarization, which is an equal superposition of R and L. And this will promote this qubit to the excited qubit, and keeping the relative phase between the up and down components exactly the same. This is very important. So you see up excited minus down excited. And when this state decays back after about 1 nanosecond, it emits a photon. And the state that we end up with is an entangled state of a photon and a spin. Up R minus down L. So we can repeat this process again, and excite again, and collect the photon which is emitted. And each time we add another photon to the chain. So after one more step, we obtain this GHZ state of 3 qubits. And we can continue and generate more generalized GHZ states of more of n qubits. In principle, we can repeat it indefinitely. So this is the experimental system, very quite simple. So we have the quantum dot. We have a bunch of lasers that provide us with a pulse sequence. We have a wave plate where we can vary theta from 0 to 2 pi. We have a polarizing beam splitter. We have 2 detectors and some time tagging device, a correlator, with which we can measure coincidence rates of several photons. So first we apply a pulse, a photon is emitted, transmitted through the waveplate, and randomly chooses between the edge and the arm. Another pulse, we apply another pulse, another photon is emitted. Again, this time for the example, let's assume that it chose the V arm, and the last pulse again is used to project the state of the spin. Let's assume that it chose the edge arm. So now we look at this sequence of edge V edge. Okay, so it's one of 8 different possibilities. Okay, of permutations, and we expect to if we now count how many such coincidences we observe in a second, for example, we anticipate to see it varying as a cosine twice theta when we vary the theta. Okay, so here are the results. So this is the control case of only 1 spin and 1 photon. The phase accumulated here is only 1 times theta, and here, as we expect, as in the first slide of this presentation, you see 1 oscillation. Okay, 1 oscillation for each projection possibility. You see here edge, HV, VH, and VV. Okay, and we can sum those 4 curves to obtain a degree of polarization, which is defined by this, and we obtain one nice oscillation. Now we repeat the experiment with the GHZ state with the spin and 2 photons, and the phase cumulative is twice theta. And this time we measure 8 different curves. We sum them up in a similar way, and we see a double oscillation. Okay, and by this we demonstrate that the double frequency is essentially again in the precision of theta. So here again are the results on one plot, and you can see that from the case of just one photon and two photon, there is a reduction in the contrast. Okay, you see the visibility of the oscillation, or the amplitude of the red and blue. The blue is reduced a bit. Okay, this damages the precision. Okay, because it reduces the slope, and we want to avoid it. And you can think that if this happens only for two photons, what will happen to 10 and 15 and so on? We will completely lose the visibility and it will be useless. So we were trying to fight very hard now this is a result of a decoherence in the system. Okay, so we were trying to find ways to beat this coherence and to do something better, and we actually did. Okay, Dan and Zuen succeeded, and so far I did not mention at all what two-level system I was using. So let me say it now. So those results were obtained for the dark exciton occupying the dot, and it turned out that if we use a heavy hole and we use a magnetic field to split it, we can obtain better results. So you see here, this is the same scale. You see here that if you compare the blue and the red curves, we see a much less drop of the visibility. Okay, and then we extrapolate and see that this visibility is much stable over the number of photons. So the reasons why the hole provide better coherence are very interesting, but I will not discuss them here. Okay, so with this, I'd like to thank you.
Thank you. Giora, questions? Yes.
Hey, yo. So you presented you get a gain of 12 of the JZ side that you managed to produce, right? Two in this case. So what actually limits the size of the JZ state that you can, like how many photons you can entangle and therefore give a gain? So if you want a 10-fold gain, then you need 100 photons, right? How feasible is that?
So there are two aspects to the answer to this question. One is how many photons we can actually measure in the lab in terms of signal. Okay, because the more correlation you're looking for, the smaller is the signal. It's hard to obtain statistics to prove your point. So to generate something is easier for us to prove that this is what we are generated. Okay, this is one thing, and the other thing is the coherence, as I was saying. So the visibility. So in the first experiment that I showed, we anticipated after 5 photons there will be the contrast will be 0, will be decayed to 0, and with the second experiment with the hole, it is assumed to be 15, right? Something like that. Okay.
So 15 qubits or 15 photons that you're correlating?
The difference between them is one spin, so it's okay. 14 plus 1. Yeah, this is the extrapolated the estimation. Yeah.
And what's the scalability costs of such expansion? So moving from 1 quantum dot 2 to 14, let's say, can you reuse some of the equipment, or the apparatus scales?
No, the quantum dot is only one. Yeah, the apparatus. No, you just have to. You have to make take the pulse sequence and place their 15 pulses. Each pulse provides you another photon. Mm-hmm. So in principle, just more pulses, you get more photons.
So you're not scaling the the apparatus. You're just
Yes. You just have to introduce more pulses. You can use the same laser. You split. You have to introduce delay somehow between the pulses. So you take a pulse of the laser, you split it, you introduce delay between the pulses, and you add the pulse to the sequence. So if you are efficient with your power, you don't lose power, and you minimize the power you need to excite the dot. So in principle, you can add as many pulses as you want.